Okay, so as I said before, and what I mean by before is our course is broken into several scales. And so our solar scale, our stellar scale, our galactic scale, and our cosmic scale. And we finished with stars last week with our exciting tour through general relativity and space-time, and also looking at black holes. Now, it's good to learn about general relativity in the way we did, not only for black holes, but it's really the model that describes how things move within galaxies as a whole. And it's the model that helps us understand things at the galactic and cosmic scale, the motions of galaxies and things like that. But before we look at galaxies in the universe at large, we want to, as always, study the closest galaxy to us, which is, of course, the galaxy we live in. So the numbers get really big here, and there's a lot going on. If you think the stellar scale is amazing, the galactic scale is almost incomprehensible. And looking at galaxies as separate from ourselves as these sort of pockets of structures of collected stars is only about 100 years old. It was only in 1920 that the Andromeda galaxy was experimentally proven to be a different object distinct from our own collection of stars, our own Milky Way galaxy, and that's when this term really kind of took off. So again, when you're thinking of something like this isn't ancient knowledge that people had or things that people considered in experimental detail until the 20th century. But we will, of course, start, even though we have sophisticated instrumentation to make experiments with this stuff, we will start with what we can see, all right? So, of course, the first sensor is your eyes, and we want to see what our galaxy looks like. So this is a good place to start. On a really clear night, the Milky Way galaxy appears in our sky as a faint band of light, all right? And it's faint because there's so much dust in between the stars that visible light gets mostly scattered, all right? And if visible light gets scattered, we can't see it. So you'll notice it looks a bit like spilt milk, hence the name. And if you'll recall from our discussion of how astronomy was developed in the beginning of the semester, we saw that Galileo was able to resolve with his telescope that instead of being a distinct Milky-like object, that this was indeed in a collection of individual stars that were far away that they couldn't be resolved. And that was a big step in getting a much larger perspective of the universe, all right, and allowed in people's minds for stars to be much farther away than they previously thought, which allowed them to be much bigger than they previously thought. You have to look at it from their perspective. It's really difficult to imagine something as big as we know a galaxy to be when we ourselves are so small in comparison. It's really, really difficult. So we want to keep that in mind, okay? Now, let's go through and get a sense of that scale, all right? So the only term we'll learn about, we already talked about the dust obscuring, scattering light, but the interstellar medium is the sort of space between the stars in galaxies. And what we want to keep in mind with this interstellar medium is that galaxies we'll see facilitate are the structure in which we live. If you've ever taken a biology class, you can think of it this way. Imagine the cells in your body are like the stars in our galaxy, all right? Your body would be the galaxy. It would be the structure that facilitates cell creation, life, and death, which is what your bodies do. So in some ways, our stars are like the cells in the galaxy, and the atoms in those cells would be kind of like, I don't know, the very large planets, or maybe even the people, although that scale still doesn't do it justice. But if you can imagine that, us understanding and perceiving the structure of the galaxy is like the atoms in our body having opinions about people, all right? and those atoms can't even comprehend the larger scale of our universe. So that's kind of one way to think of it with these scales. And we'll look at the structure. Now that we've seen what it looks like from space, we can look at a model of our galaxy. And this is not our galaxy, but this is a model of what we think our galaxy looks like based on what we can see. All right, because we're obviously not outside the galaxy. This is a picture from outside the galaxy. So it's an edge-on schematic. So you'll notice that we have certain structure. All right, so we have these halo stars around the galaxy. These kind of look like our Oort cloud. We have a disk, a flat disk structure, which is pretty blue. And then we have a bulge in the center. So those are our three qualitative properties of galaxies. Now, galaxies sort of look like solar systems, but they're very different. So the center of mass of a solar system is in its star, right? So remember, our star is 97% of the, or 99, over 99% of the mass in our solar system. The bulge, even though there are central large objects, and we'll see that later, that there is a large massive object in the center of our galaxy that is probably the largest single object in the galaxy, it is not large enough to compare to the mass of the rest of the galaxy. What that means is that the center of mass is not at the center of the galaxy. All right, it's distributed evenly, of uniform density. So making everything into a point doesn't quite work here. All right, but let's get a look at some of the scale. So I want you to look at the smallest part of the disk. So if you were to send a signal, a radio hello world, from a signal today, it would reach the top of the disk in the year 3020. All right? Another way to look at that is that if we received a signal from another species, say we were here on this end of this bar. Oh, I don't have my pointer here. If we were on this end of the bar, to get to the other end, it would take you know, it would have had to been sent in the year 1020. All right, to get some more perspective, if we could send signals in space from the first cave painting when it was made was beamed into space somehow, it would only have gotten about here in the galaxy, that signal. All right. So you'll notice that the width, the long width here is 100,000 light years. Keep in mind that if you're being very, 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 very generous, sort of modern creative humans that make art and write things down is 30,000 years old. And that's being extremely generous on the timeline. Some have it as low as 12,000 to 10,000 years old, or even 5,000 or 8,000 years. So you know, the scale is just mind-bogglingly huge. And the fact that there's structure at this distance too, you'll notice you have that bulge, halo, and disk is pretty spectacular as well. And you'll notice the sun is right here, but I want you to keep in mind the scale of the universe. Inside this little point here, inside that 1 pixel, there are more stars visible in that pixel and contained in that pixel than we can see with our naked eye. So every star we've seen is in that little tiny fraction of the galaxy. That's how much is visible to us. Okay? So galaxies are huge, for lack of a better word. And we have globular clusters and satellite galaxies, but those are different things. Now let's look at it from an edge-on perspective. Okay? When we look at it from an edge-on perspective, we can see that the bulge is still yellow here, but the disk is a lot more vast, right? The disk is very big and very blue. And if you remember from looking at stars, my thought question, or my question to you all is, are the stars in where do the older stars live? In the bulge or in the disk? Just by looking at colors. What do the colors tell you? We're gonna have older stars in the spiral arms, in the disk here, or in the bulge. See what you remember from stars. Don't be afraid to use that chat. It's quiet in here. Nothing has been said since you joined the chat. Anybody? Can you all hear me? All right. Well, I give it another minute, but then I'll go on. Which stars are older? Which are younger? Yes, Margarito.
You can hear me, right?
Yeah.
Halo, right?
What?
I said
Well, we
Halo.
haven't talked about the halo. We're just the disk and the bulge. The halo's a
The
different.
disc. What about? It could be the disc.
The disk for what? Older or younger?
I'm going to say older.
Ah, that is not correct.
Okay.
But good try, and thanks for chiming in, though. I don't want you to not answer questions again. So it's because the color. Remember, if we look at our Hertzsprung-Russell diagram, older stars are yellow, right? Because they last longer. Blue stars, or more bluish stars, usually represent more mass, and we can tell the age of a group of stars by the color. And blue stars are bigger and brighter, and they don't last as long. So we can tell that younger stars exist out here because they just don't live as long. Once a galaxy ages and all those short-lived stars die out and can't be formed, we'll see some interesting things happen. The disk sort of goes away and becomes more yellow. So the halo is a little different, though. The halo actually has a lot of the older low-mass stars, and we'll talk about that in a minute. Because the center of mass is not at the center of the galaxy, right? There's a lot of weird orbits. So in the halo, which are these big giant blue orbits, and in the bulge, the orbits are pretty random and they go sort of all over the place. In the disk, though, which sort of treats the center of mass not as a point but as the bulge itself, you get these carousel-like motions. Notice that it goes up and down and around. All right, and that's how stars travel in the disk. But outside the disk, whether you're in the bulge or in the halo, your orbits are fairly random. Okay? And we notice again that stars in the disk all orbit in relatively the same direction with a little up and down motion. And so that tells us that angular momentum conservation played a very important role in the formation of the galaxy. All right, and we'll talk about that in a minute. So now if you look here, you'll notice that, like I said again, there's our sun, and this little tiny dot expands to show what we see in the night sky in our local neighborhood. And they appear to move randomly from one to the next relative to each other, but as you step out and look at them all at the same time, they do go in the same direction, or at least that's what the telescopes say. And we have an orbit around where we are in the Milky Way of about 230 million years. All right? So, but more importantly, we can tell from where we are, from extrapolating our orbit out, we can estimate how much mass we encircle, right? Or how much mass is encircled by the sun. And within the sun, there are 100 billion solar masses, right? So that means that 100 billion times the mass of our sun is inside. And when you do that to the outside, and you realize that our sun is a big star and fairly rare, you get that there's somewhere between 100 to 500 billion stars in the Milky Way galaxy. All right? And again, I want to remind you of the difference between a million, a billion, and a trillion. because a lot of those things are looked at, especially because we only look at them in terms of money. So a lot of the times it can seem like million, billion, no big deal. A million seconds, I always like to do this in terms of time. So if you don't remember this analogy, I will, or it's not really an analogy, or this comparison, I'll do it again. So a million seconds is a little over 11 days. In fact, I'll calculate that one out. I'll do the calculator because I can't remember the exact parts. I don't remember whether it's 11 or 18. Yeah, question?
Was it gonna be like a billion seconds, 31 years?
Well, a million seconds. Let's do the calculation really quick. A million seconds is not 31 years. A billion seconds is about 31 years.
Yeah, that's what I was saying. A billion seconds is 31 years.
Yeah. But let's do it. Let me get the calculator so I can get the actual numbers again, because I haven't done the calculation in a while. It would be fun. So there's 3,600 seconds in a day. Divided by 3,600 times 24. Hold on, I did that wrong. So hold on, 3,600 times 24. So 1 million divided by 86.4. No, that's the problem with this stuff. I'm just pressing buttons wrong. So right, so about 11.5 days is a million seconds. So a billion seconds is going to be 1,000 times more days. So that'll be 574 days, which divided by 365 is 31.7 years. And a trillion seconds would be 31,000 years. All right, 31,700 years. So keep that in mind, that when we talk about billions, hundreds of billions, or almost at a trillion solar masses here, how much bigger those numbers are than the previous one. Because there's a lot of stuff that says, well, Jeff Bezos will be the world's first trillionaire. And you should keep in mind exactly how much a trillion really is. It's an enormous number. Okay? So, the orbital velocity law, that's just what gives us our mass number for what's orbiting inside the solar system. But now that we've seen so are there any questions on what the galaxy looks like and sort of what we've seen so far? Before we go into, I'll go to a picture of the galaxy. That's better. Are any questions on what we've seen and looked at so far before we move on? No? Good? Okay. So now that we've seen what galaxies look like, we want to look at what our modern observations tell us about galaxies. What can we say about the structure of galaxies that we see? And what we'll find that's interesting is that galaxies give the stages of star life context. Because stars, when we look at them individually, we know they're born, they live, and they die, but we don't know how the universe facilitates that process. It doesn't happen in a vacuum. It happens as part of the galactic structure. So you'll notice they call it galactic recycling, all right? So we want to see how stars beget new stars, all right? And we'll see where star formation happens and things like that. So we have a summary slide here that's first, and what we'll see is that star life, if you recall, we always talk about stars starting in a nebula of gas that condenses to become hot, and that is collapsing, and then ends in either a planetary nebula or a supernova, which expels gas. So all we're missing is the steps of how we get from the explosion back to the collapse. So we've already sort of looked at this part of it, right? This was the last previous chapters. Now we'll see what happens to that gas, and we'll understand that the exploding gas of old stars or dying stars will lead to the cycle that allows new stars to form. And we're also going to see that, much like everything, star formation can't go on forever. There is only a finite amount of gas available in the galaxy to form stars. But that will be a topic probably more for the next chapter than this one, which we may get to. I don't really know if we'll get there today. We might. So we're going to look at this star gas cycle, and we're going to look at it in steps. We're going to go quickly through the ones we've seen, but appreciate some of the pictures. And then we'll spend some time on the ones we have not seen. So high mass stars have strong winds that can, so we have solar wind, or besides dead stars, like from planetary nebulas and supernovas, live stars in their main sequence have very strong stellar winds that blow out gas. They can create these large bubbles. If you think you can make a large bubble, this is a very, very large bubble that blows gas into interstellar space, that space in between the stars. All right, so this is stuff that can happen during the main sequence. And that's all a function of the solar wind. Of course, after they're done with the solar wind and the stars die, they expel an extraordinarily large amount of gas and elements. We have here a planetary nebula. This is a pretty cool death knell of a low mass star. And then, of course, we have, I think this is an X-ray image of a supernova that shows us the very hot gases for a supernova. Now, keep in mind, an explosion like this is easily bigger than our entire solar system, right? So we can see newly heavy-made elements and things like that. And this is all being exploded out into interstellar space. Now, what's new this decade, what's exciting, is that teaching this class, like in just 5 years, since 2015, this discussion stopped here. And you'll notice your book, we don't go much farther. But now we're able to study in detail collisions between neutron stars and black holes and neutron stars and white dwarfs. That, you know, a lot more of collisions are actively being able to be observed, both with stronger telescopes and gravitational lensing, or gravitational waves. Gravitational lensing is something different, with gravitational waves. And so we're able to get a lot of information, and we can see that those processes also are sources for large amounts of heavy metals. And in fact, one neutron star collision, neutron star collision, they were able to observe a chunk of gold or something like that, gold or other rare earth metals, like stuff that's very rare here, the size of the Earth, right? That just flew out of that collision. So I mean, these things, you know, there's all sorts of interesting ways to create heavy elements and expel gas. And the supernova and the planetary nebula are they're two of the more common, but there's certainly other mechanisms that go on. So we can see here the supernova remnant cools as it begins to emit visible light and expands. The new elements made by the supernova mix into the interstellar medium. So how do we see this stuff? Well, it actually all goes back, sort of as always, to that light and matter chapter. We can see that we can see from the spectra of these gas clouds what elements are actually in there, and from the intensity of that spectra compared to other elements, how abundant they are. So we can look at these gas clouds and just see what's there, and we can look at the spectrum from them. There's an interesting page on the website Reddit called Space, where it shows people taking long exposure satellite images. You have to remember that with these visible light images, you might not see these with your naked eye because your eyes aren't big enough to collect all the light. These are real images, but your eyes can't collect all the light in that short amount of time. When you use cameras and binoculars, you yourself can recover these colors by taking long exposure images. And you can see how impressive the night sky really is. Okay. Now, multiple supernovae that can happen in the disk will start to mix together to create these sort of big plumes from the disk. All right? And this can sound just like an idea, but as we're going to see, these are all things we observe. We can actually observe these plumes shooting out of the disks of our galaxy and other galaxies. All right? And so these huge bubbles sort of explode out, and they cool down as they explode out, as they expand, and then as they expand, they fall back into the disk. All right? So these are the hot clouds rising and pluming out, and then these cool clouds fall back into the disk. All right. So atomic hydrogen, H2 gas, forms as hot gas cools, and this allows electrons to join with protons. And molecular clouds form next, so after gas cools enough to allow atoms to combine into molecules. All right, pretty simple ones, but molecules nonetheless. And again, remember that spectra is defined by electron transition. This is why, and this comes back to quantum physics. So the spectra is predicted by the distribution of energy levels of atoms and molecules. And so that's the connection back to quantum mechanics of what we're seeing. That stuff isn't predicted by Newtonian mechanics or Newton's physics. You need quantum physics to predict those spectra. And if you remember, quantum physics gives us all those fun stuff like the Heisenberg uncertainty principle and the Pauli exclusion principle, which helped us understand the difference between white dwarfs, neutron stars, and ultimately black holes. So we can see that these molecular clouds contain mostly hydrogen. Hydrogen again and helium are the most abundant substances in the universe. About 1% carbon monoxide, but small amounts of many other molecules. Now keep in mind, all right, when you're wondering, well, gee, that doesn't sound like a lot, I get you, but remember that the sun is 99% of the mass in the solar system. So that means if every heavy metal and element on Earth if the planet, if all were made of all the other planets, like say all the other planets were made of these heavy elements, and the Earth is not even the most massive planet, that would still be less than 1% of the mass in our solar system. So keep that in mind, that if you have a piece of metal or a gold band or something silver, anything heavier than iron, or more, not heavier, but more higher on the periodic table than iron, you have, it's very rare. It's something that is very rare. And is not abundant in our solar system or in the universe as a whole. Okay, so gravity forms stars in these gas clouds, and so basically as those gas clouds cool, the mass starts to gravitationally attract and collapse. So you can see a collapsing gas cloud here, and then this will form stars. Now I believe we're getting to the pillars of creation. Hold on. We should be getting to the pillars of creation. I guess we looked at the pillars of creation when we looked at star formation. Yeah, no, we did. But that's more of a galactic thing. So if we look at our galactic recycling, this is sort of a bigger picture of the pillars of creation. I think they're in there somewhere. But if you remember, when we saw the pillars of creation, this is invisible light, right? So if we look at infrared, the light can go through these gas clouds, and we can actually see stars forming in these clouds. And that's what I mean about our vision being limited. And in fact, when we can't see all of galactic recycling with our naked eye, but what we are going to do is we're going to look at how we go through these steps, and I'll repeat them in a minute. And we're going to look at the galaxy sort of edge on, like we did before, but we're going to look at it through many parts of the electromagnetic spectrum. So, and each part will reveal a new feature of the galaxy. So, but before we do that, our summary is stars make new elements by fusion, right? The dying stars expel gas and new elements, producing hot bubbles about 1,000,000 Kelvin. The hot gas cools, allowing atomic hydrogen clouds to form. It's from 10,000 down to about 100 Kelvin. Further cooling permits molecules to form around 30 Kelvin. And then gravity will form new stars in those clouds and planets and everything else. And then once those form, you get back up to the top to fusion. Okay? And now we'll get to what I was discussing, which is what we're looking at here. You'll notice you can see the visible picture of our galaxy. And this is a version of our galaxy being on the inside. All those features aren't as defined as they were in the schematic. But we're going to look at it in, you'll notice that all these pictures look different. They're all the same picture, but in different wavelengths of light. And it's this picture, because we're not ready to, this is one of my favorite pictures in the course, because it's helpful to look. We often look at a lot of things in different spectrum where they're useful, but a galaxy, and it just takes a while to get here, is useful for understanding just how different the different parts of the E&M spectrum are. And so we're going to go through each one and look at them. Okay, so you'll notice this is what this is what the night galaxy looks like in the night sky. So this is what our galaxy looks like with visible light. You'll notice we can see some hints of a bulge, but it's sort of hard to make out any defined structure because we just don't know what's going on. And we know by being able to look at other parts of the electromagnetic spectrum, we know that that there's more going on here, and we'll see that in a minute. So we'll notice we can look at short wavelength infrared light. And now when we look at short wavelength infrared light, the structure of the galaxy, or at least some of it, becomes more obvious, right? You'll notice we have a bulge. We have light halo stars. These are our satellite galaxies around here. And you'll notice that we can see a bit of the structure. It doesn't look quite as fantastic as that schematic, but we start to see that our galaxy has structure. It's not random spilled milk. Okay? And again, infrared doesn't scatter like visible light does. The infrared just goes straight through the dust. That's why we can see this, this picture. And now if we look at X-rays, well, X-rays are pretty interesting. We can see that in the halo, there's a ton of hot gas. So these are the gases from those bubbles expanding out, but you'll notice in the center, it's a bit cool. All right, so this tells us that the idea is not a bad one of gas rising and collecting going out of the disks. We believe that's true because that's what pictures tell us. Okay? Now, if we look at 21 centimeter radio waves, which are by atomic hydrogen, this is a preferred wavelength to look at because it's specific and universal, right? Hydrogen is the most abundant substance in the universe. Any civilization that, like ours, if there is a civilization out there, should be aware of this 21 centimeter radio line, and it's the best way to communicate with life is on this frequency, this 21 or this wavelength. But you'll notice when we look at that, we can see the hydrogen here in the band across the disk of the galaxy, and we can see that that these will come from warmer gas clouds. So these will come from collapsing gas clouds and star-forming clouds. All right, you'll notice we see them more in the disk structure. They're not really in the bulge or the halo. All right. And now we can look at radio waves from carbon monoxide instead of hydrogen, and they show the location of these cold molecular clouds. You'll notice the cold molecular clouds are either falling back into the disk or they're above the disk falling back in, as compared to those hot clouds when we look at X-rays, which were all over the place. Now, we can further look at at long wavelength infrared emissions, and these can show where young stars are heating dust grains. So you'll notice a lot of that heating is happening in the disk and expelling out. And now we can look at gamma rays, and we'll notice that our gamma ray sources from supernova are all coming from almost exclusively the disk. You got a few bright spots out here, but just about everything is in the disk. So when we form all that together, we get, I want to go back to the composite so you can see the different, that we can construct our system star recycling from direct experimental evidence by looking at the dynamics of energy, or not, but a particle movement in our own galaxy, right? And how those particles are at different temperatures, which we can remember, we can also tell the temperature of the gas from its black body spectrum. Okay, so you'll, and I want you to keep in mind that most of the things we look at for data have to do with all that stuff we learned in the interactions of light and matter chapters. Spectra tell us what they're made out of. Temperature will tell us how hot the gas clouds are. And then from there, we can use what we know about gases in the laboratory, which is extensive. Studying gases is a huge field in both physics and chemistry. Then from there, you can put together a fairly compelling picture of what's going on with galaxies and star recycling. So are there any questions this far? I'm going to get back to this picture. We're good? Okay. So we want to look at where do stars tend to form in our galaxy. We already sort of answered that question. Does anyone remember the answer? So your choices are disk, bulge, or halo. And I told you halo stars are very old, so we can mark that one out. So where were the young stars? No, they weren't in the halo. They were in the disk. Disk, disk, disk. Remember, we can tell that from the color of the stars in the disk. So the disk stars are bluish, which means that there's a lot of young stars. And remember, if there's young stars, that means they formed recently, right? High mass stars are much brighter than low mass stars. They don't live as long. So if you see a lot of high mass stars that are overpowering all the low mass stars, that means those stars are young and they formed recently. Therefore, you can conclude that star formation is happening in the disk. Okay? So we can see that from these nebula pictures. And again, you know, they're just trying to lead you to that point, right? That in the nebula you see purple and blue, and you'll see that happens in the spiral arms, not in the bulge, right? The bulge is yellow, which means most of those stars are low mass and older. Okay, there's no recent star formation in the bulge. Okay, so a way to think of spiral arms is that they're waves of star formation, and as the galaxy ages, the spiral arms almost certainly decrease and get thinner, and you end up with a mostly bulge galaxy. And we'll talk about that in a little bit. All right. So we've already seen this stuff. No point in beating a dead horse to it. So now that we've seen galactic, or how stars form in galaxies and where stars form in galaxies, we want to try and take a stab at where the galaxy came from. Now, the model presented here is not great. It's extremely oversimplified because galaxy formation is hard. But we look at, what we want to do is we'll come up with a hypothesis based on the features we see. So we'll notice that the galaxy has a flat shape, much like our solar system, and appears to have a central region like our solar system. So this seems to tell us that, and we also see that in the halo, we have old low-mass stars. And we also see, another observation we make in the halo is that a lot of the stars don't have a lot of heavier elements. This seems to indicate that they're older stars, right? Because they didn't benefit from other star cycles, star recycling, delivering higher, heavier elements to their systems. So when we look here, disk population, that we have stars with compositions like the sun orbiting near the plane of the galaxy, a mix of young and old stars. In the halo, scarcity of heavier elements orbiting at random inclinations to the galactic disk. These are all older low-mass stars. So basically, when you put that with the other features together, the idea is that the Milky Way has shrunk into a disk, right? That the Milky Way was spherical and star formation was happening, and then quickly, much like our solar system, became a disk. And once it became a disk, you had the stuff that had formed out by the, you have sort of the leftovers of star formation out in that halo region, and then you have everything else in the disk. So they often start with, I call the intergalactic fart, this giant gas cloud, and they have it collapse into a galaxy. Now, my problems with this stem from the fact that the universe was much more, the galaxy had to have formed maybe 10 to 12 billion years ago, and it seems like galaxies sort of just formed all along the same time, and 12 billion years ago, the universe was a much different place. It was much younger. And looking at this region of galactic formation is something we struggle to do. When the James Webb Telescope comes online, I'm hoping it answers a lot of these questions. So it's the reason I don't like to think of it as a large gas cloud is because in my mind there's a point from between 300,000 years to 1 billion years where everything, the universe, is this giant protogalactic gas cloud, and then as it expands, gravity keeps some of it locally together and then disconnects other parts of it, locally. What I mean by that is that parts of it would be causally unconnected because they're moving away from each other faster than the speed of light. And so as the universe gets bigger and parts of it move away from each other faster and faster, some of this gets locally bound, and then other parts of it go away. And then once it's locally bound, then it can start collapsing. I can tell you this, when I was in college, when I was your guys' age, galaxy formation was a huge active field. And from what I understand about astrophysics today, it's still very active and new things are being discovered. So we present a simplified model here, but if you start very confidently and being very cocky saying this is how the galaxy formed, and someone tells you different, who's actually studied this a lot more, I'm very much not going to be surprised if a lot of this is wrong. But for your exam, for your quiz, start with the cloud. It looks like solar system collapse. All right? And then eventually you get this nice galaxy, spiral galaxy. Even the book says this model is oversimplified. They've never said that before, but it really is here. There's a lot of nuance with galaxies. Also, as we'll see with galaxies, what we're seeing right now and the observations we make are only half the story too, because a large part of galaxies are dark matter, which are a dominant force in their structure than the stuff we see. So any model we talk about in this particular chapter, until we talk about dark matter, which we'll do the last day of class, isn't going to really cut it because it's missing a ton of information from that. But it's basically a model that is consistent with other observations. All right. I just like looking at this picture, really. I don't have much to say. You can look at these clumping star formations. That halo stars are very strong. All right. So now we get interesting. As I told you before, I alluded that interesting things are happening at the center of our galaxy, and while they aren't, how should I say, Well, the center of mass of the galaxy isn't at the center of the galaxy. The most massive object in the single object in the galaxy, likely anyway, very much is, or the largest object we've detected in the galaxy. And this brings us to a new type of black hole. So we talked about stellar black holes. We will now talk about supermassive black holes. So we want to first look at why do we think the object in the center of our galaxy is a black hole? Well, one reason. Remember, stars can only max out at about 300 solar masses, right? Anything else, radiation pressure would start to blow the star apart. So there's an object, so we want to keep that in mind. So we can see with infrared imaging here, we can see a zoomed-in picture, a high-res picture of the center of the galaxy, and we notice these rapidly orbiting stars. Now you'll notice that the same point is a focus for each of these ellipses. All right? And we can see that all of these stars orbit around the same central mass point. So there's this object here that's gravitationally affecting the orbit of actual stars. So that's impressive. It must be a very big star, one would think, right? Well, we could look at it, and this is just a zoom in of the center of the galaxy to get back to what we just talked about. So we can look at the pictures again. We can zoom in the central region of our galaxy with X-ray and infrared observations. And then we get our picture here. Now, we could say, well, maybe it's just the biggest star in the galaxy. But the object, remember, we can use Newton's laws to guess at the mass. And the mass at the center has 4 million solar masses. So that's the mass of 4 million suns. Way, not only bigger than the upper limit of stars, but so far beyond it that it clearly can't be a star. So if it's not a star, and it's not a dead star, it must be a black hole. Remember that fundamentally black holes mean that something exists that's beyond our ability to describe it with general relativity and quantum physics separately. A combined theory of those two is required. So we can see this here. Radio light reaches us from the galactic center, so we can see stuff like that. These are radio pictures that we can see that we can see the magnetic fields that are sculpted as they where those radio waves leave the center of the galaxy. And we can see other dynamics of gas motion in the center. We can see it swirling around that center of mass. And we also think we can, this is a simulated image, we want to see if we can make a better image of the central black hole to figure out the exact size of its event horizon. So a lot of interesting things going on here. So the stars appear to be orbiting this invisible thing, and again, 4 million solar masses. That's a lot. Let's see. What we're looking at here is an X-ray flare from the galactic center, and this suggests that tidal forces of this black hole occasionally tear about chunks of matter, stars that cross its path. And the bigger the black hole, the easier it's going to be for stars to cross its path. And remember, the star population is much more dense here in the bulge. Okay? So that's it for that chapter. Let me see how big the next chapter is, because I think we might just go on break now. So what I want to do is, I know we usually take a much longer break, but this is the part of the semester that actually naturally does go kind of fast. So I don't want to give you too much too much information, because a lot of this is enough to think about. So, you know, we can do a hard stop on after we're done with the next chapter, with chapter 16. I don't want to start talking about everything. You know, it's too much information to think about. But let's take a 15-minute break, and we'll come back and we'll see how far we get. That way, if we finish this, we can just end a bit early. But this chapter is, I think, a little more, yeah, this is a little more meaty than the previous chapter. So I don't know that we'll get through it as fast. But let's take a 15-minute break, and then we'll come back around 4:35, 4:40, maybe 20 minutes, and then we'll get started on this chapter, and then we'll see where we get to by like 6:10. And if we're making good progress, we might just power through, or we'll see how it goes. Okay? So I'll see you all in about 15, 20 minutes. All right, everybody, I am back, and we will continue our discussion on galaxies. So now we get to some of the really deep fields of the universe, and we're going to bridge to our cosmic structure. Now, this is probably one of my favorite photographs. I've been looking at it for about 20 years, and that still is just amazing to me. So what are we looking at here? We are looking at one of our deepest images of the universe that we can see in visible light. And it shows a great variety of galaxies. So keep in mind that every dot here is a galaxy with at the very smallest galaxies have maybe tens of millions, the very smallest one. Most galaxies have hundreds of billions, and the largest galaxies have trillions to tens of trillions of stars. So the Milky Way is not by any means a large galaxy. So our deepest images show the great variety of galaxies, some of them billions of light years away. And in fact, we'll watch a video as soon as we introduce this section of different types of galaxies. I'll send you a link for a video to watch so we can get some perspective on different sized galaxies. I just want to see where a good cutoff point for that would be. Probably after this section. Okay, so let's take a look at some of the stuff we're seeing in this picture. All right, so basically we do all the stuff in look back time, and the galaxy's age, its distance away from us, and the age of the universe are all closely related. All right, so what we need to look at is not only can we see these galaxies, but when we look at a picture like this, we can see the different distances and the age of galaxies. We can then figure out the patterns of galaxies in the universe, and they start to get, and that's the bridge that takes us to our galactic scale, to our cosmological scale. All right, where we look at the universe as a whole object, and we make observations from telescopes that tell us about the universe. Now, we see all sorts of different patterns. You'll notice I told you about galaxies that are sort of all bulge. These are called elliptical galaxies. And we can see these different types of spiral galaxies as we go through. We don't have we can look at types of galaxies, but and we'll see the different patterns that we find in them, but they're not quite as rigorous as stars, meaning we don't have like a Hertzsprung-Russell diagram that gives us that level of detail of galaxies, but we sort of loosely formulate them in certain ways. So what I want you to do is I want you to look at this Hubble Ultra Deep Field, and I want you to quickly for the next, I want you to take 5 or 10, let's do 10 minutes, because I think we have plenty of time, and I'd like you to do this on your own. I'd like you to just make bullet points. It doesn't have to be complete sentences. Write about the different things you see in this picture. And we'll see how many we cover, and then we'll see what we didn't cover, what you see that I don't cover at the end. So take about 5 or 10 minutes and just take a look at this picture and see what kind of different galaxies you find. You know, put on your astro hats. How would you analyze this picture? I know there's a lot, but that should make it easy to write down what you see. What'll really blow your mind is how little portion of the sky this is. This is only something about the size of, I think, a dime or something in the sky, maybe even smaller. Now, I have to look it up. I'll do that while you guys are looking. But just make some observations. Notice the different kinds of galaxies you see. Again, there's no right or wrong here. Just write down what you see. So as far as I can tell, it's about the size of a soda straw. Yep. But it's hard to say how much longer, right? Because high mass stars don't last very long. So it could be that all the gas was ignited at one time. Well, all of these are very far. In fact, this image is as far back as we can go in visible light. To see back any further, we need infrared, which is why the James Webb Telescope is more infrared than visible light. Because the universe will be too dense. All right. So let's take a look at some of what we see and the types of galaxies we'll see in here. And let's see if they, well, yellow stars last longer than blue. But yellow stars last for billions of years. Blue stars last for millions of years, right? So it doesn't mean they're necessarily old. It means that star formation has ceased, right? So there's a few reasons that could happen. So and in fact, when we're looking back in time, because this is in terms of look back time, we know we're actually looking at a young universe here. All right. So they can't be that old, but all of the high mass, short-lived stuff certainly would have had time to have extinguished out, particularly if galaxies collide, which is something we'll look at, and ignite all the dust and gas. So let's take a look at the type of stuff we see. Okay. So first, you'll notice we're going to pick that type of galaxy, and we'll zoom in on it. And that is a spiral galaxy. So you'll notice it has the features that we looked at for our own galaxy. It has a bulge, and it has spiral arms. You can see a little bit of a halo, but not much of one. So we can see that type of galaxy. And there you can see there's a few of them around here. Yeah, a few spirals. Now, you'll notice we're on a different kind. You'll notice right away it's not a spiral galaxy, right? It doesn't have the same features as the spiral galaxy we're looking at here. So let's look and see what this is. This is an elliptical galaxy. Now, an elliptical galaxy, you'll notice, is almost like a diskless galaxy, right? All bulge, no disk. All right, you'll notice that disk part is absent. There's actually a type of galaxy called the lenticular galaxy, which is where it has a fading disk and almost is on its way to becoming elliptical. All right, and now if you look here, you'll notice this doesn't look like a spiral, but it doesn't look like an ellipse either. And anything that's not spiral or elliptical is called irregular. And irregular galaxies are thought to be the remnants of galactic collisions or torn apart galaxies, things like that. But they're still big enough to be gravitationally related, but they have irregular shapes. So they're called very unimpressively irregular galaxies. So what I want to know is, did anyone sort of see anything in here besides these three? That's the type of things we're doing. I want you to sort of look at it again now. We'll take those back. Those are the types of galaxies. But I want you to see if you can find other irregular, spherical, or spiral and elliptical galaxies. And I want you to see, things you can point out. We talked about colors, so that's good. Some, like this galaxy, doesn't look like it has a lot of star formation going on, the one we selected. The ellipticals almost have no. Those are even orange. They're not even yellow. But there's some bluish galaxies out here that probably have star formation going on, like that irregular galaxy had a lot of star formation going on. So those are the types of things we can tell. But anyone come up with anything that's not those types of galaxies, or have an observation they want to discuss? Right. Well, some will inevitably be brighter because they're closer. So the farther away, the more dim it is. That only makes sense. The colors, again, have to do with whether star formation is actively going on in the galaxy, right? So if we have star formation, we're going to have a bluish-looking galaxies, because remember, high-mass stars, they can live for anywhere from 1 million to 10 million years, which is very short on the galactic scale, but they outshine the low-mass stars by a lot, right? So one high-mass star can easily be brighter than 1,000 low-mass stars. So that's why the blue will be the dominant color, even though there are less of them in galaxies with active star formation. If you're yellow, like this galaxy here, you'll notice it's got hints of blue, but a lot of it is yellow, which doesn't mean necessarily that it's old, but it means that these stars are older than the low-mass stars, and it means it's not young. And what I mean by that is there's been enough time for enough gas to be used up that there's no more high-mass stars forming here. But you'll notice that you have these blue patches in the galactic arms, and those are indicative of star formation. Okay, so we need to zoom in and get a better image. The actual raw image here is extremely high resolution, so you'll notice that the zoom in doesn't suck in any of these galaxies. Interestingly, I think the irregular is kind of interesting because there's a ton of star formation, but there's no structure anymore. All right, so That's probably some fascinating stuff going on in there. All right. So let's continue on. So spirals, again, we look at our own spiral galaxy, and we sort of conclude that we're in a spiral galaxy or a barred spiral galaxy just based on the features we see of other galaxies, right? We can see what we can make observations of our own galaxy and then actually see external galaxies and say, oh, if I were looking on the edge, it would look similar to the Milky Way, right? But they still have features. Like this is a spiral galaxy that's a little more symmetrical than, say, ours. The arms aren't apparent. It's just got this sort of disk. You can see this one here. It has sort of these, it has sort of a well-defined region here, but then the disk sort of goes out all over the place. All right. Then you can see here the bulge with the older stars is a bit. They're not necessarily old stars, but low mass older stars, and these stars are older than the blue high mass stars. All right, we've already talked about that. So this is a bar spiral, and it's thought that the Milky Way is more likely a barred spiral than a traditional spiral. Okay, so it has a bar of stars in this bulge rather than just a spherical bulge. And our observations seem to indicate that we live in something that looks like this than that nicer spiral of, say, Andromeda. And again, this is a picture of the lenticular galaxy. You can see the disk is fading. There's no star formation going here. And it sort of looks like a spiral galaxy on its way to being an elliptical galaxy. All right, remember, elliptical galaxies, as we saw, don't have a lot of star formation going on. Which we can see right here, right? Elliptical, it looks like it's just the bulge, or maybe a bulge combined with a halo. No new star formation, right? And there's virtually no disk component. Now, of course, this is another irregular galaxy, which you can see this one also as well has a lot of star forming going on, but it doesn't have a shape. But everything is still gravitationally bound to something. I think studying irregular galaxies will probably be a fun thing astronomers do once they can get better resolutions or simulate them better. The problem is each irregular is unique, so you'd have to figure out. It's like solving the same problem over again for new settings. So we can see that in Hubble's galaxy classes, we have a disk dominant region and a spheroid or elliptical dominant region. And this Hubble galaxy class is a little misleading because it indicates that all spirals are bigger than elliptics. However, elliptical galaxies form both the smallest and largest galaxies in the universe. The very largest galaxy is an elliptical. And it's thought that if galaxies collide and ignite all their gas to spirals, you form an elliptical galaxy. And we'll see that in our when we watch our movie, which I'll post the link to in a second. Well, as soon as we get there to that slide, which is going to be soon. So we can see here patterns of luminosity. So let's take a look at what this says. We see our color, right? And this represents the color of the sun. And this is galaxy's luminosity in solar units and its color. So we can see here, we want to point out, so this galaxy would live here. It's large blue-white galaxies. It has active star formation. Young stars produce most of the light from small blue galaxies. So we can see that here. They're low luminosity, but very blue galaxies. We can see the largest galaxies are these giant ellipticals here. And there's virtually no star formation going on in them. It's just lots and lots of stars. And then there's smaller galaxies without star formation that tend to be companions of larger galaxies. All right, now remember, this is just a color versus luminosity chart, and you can see that this is the color of the sun. So this sort of categorizes and puts the galaxies in an organized way. It's sort of the closest that we can get to a Hertzsprung-Russell diagram for galaxies. So spiral galaxies are often found in groups of galaxies with several dozen galaxies. We're in such a group. with the big spirals are us, Andromeda, and the Triangulum galaxy, or the Tarantulum. Triangulum or Tarantulum? I can never remember. It's the third galaxy. They only care about the two big ones. Elliptical galaxies are much more common in these huge clusters of hundreds to thousands to tens of thousands of clusters. All right, so you can see there's lots and lots of ellipticals here, probably due to the collision of many galaxies in a much more dense time in the universe. If you look closely, you'll see one of the most amazing effects in physics. All right, and if you look closely, you can see it. You'll notice these sort of spiraled images that go around the center of this cluster. And we'll talk about that in a minute. So what I want to do now before we get to distance of galaxies is I want to send you the link for for galaxies. It'll be sort of like what we saw for the size of objects in the universe, but it's really going to focus on galaxies. All right. So galaxy comparison. All right, so we've got this little 5-minute video. I want the 3-minute to the 5-minute. Hold on.
Hey, kids and parents, listen up. YouTube is making so that the kids learning below this.
Okay, we're not going to have galaxies talk to us. We're going to go with this one. Okay. So it's a short video, but if everyone would click on the following link and go to YouTube, we'll check back in about 10 minutes after you finish, or it's a 3-minute video, but I'll give you 10 minutes to sort of find it and watch it. And then we'll click back and talk about those different comparisons. So I will see you at 5:17, 5:20. Okie dokie. That should have been more than enough time to watch the video. Let's see. Yeah, it's vast. Which one? The Tadpole Galaxy? Let's go back and look. Which picture? We've seen a lot of them. So I don't see one in there. The tadpole's kind of irregular. I think the tadpole sort of is in mid-collision. We don't really talk about this one. No, this wouldn't be the Tadpole Galaxy. But hopefully you saw a few things from the video. One, that even more than we talked about, there's a lot of different types of galaxies, and the smallest galaxy is only 1,000 light years across, and the biggest one is 5 million light years across. All right, so I mean they range from all sorts of shapes and sizes and all sorts of features and details. I think the Tadpole Galaxy, like I said, I'm pretty sure that one is like almost mid-collision or something. At least it looks like it. And we'll look at colliding galaxies either at the end of our lecture today or at the beginning of next week. And there's some interesting stuff. So keep in mind that next Monday we will not have class because it's Memorial Day, but they have Tuesday as a Monday schedule, so I'll be here on Tuesday with the lecture. So looking through, yeah. So now we want to look at, right, we'll have class on that Tuesday because it's a Monday schedule. But again, like always, I'll be recording, so you know, it's whatchamacallit. It'll be available even if for some reason the Tuesday doesn't work for you. Yeah, well, that's okay. You can watch the recording. It's totally fine. Yeah, I'll be here at same bat place, same bat time. So you can, like I said, the recording will be available. You can just yeah, don't worry about it so much. I'll put you down as excused. It's fine. Okay, so we now want to talk about, now that we've seen these types of galaxies, we can see that we look at them, but yeah, it's okay. Don't make too big of a deal about it. It's the absence won't kill you or affect your grade in any way. So it's, you should file it under not a big deal if you have to miss for work. But if you can, great. If you can't see it, the whole reason I record these is because I figure people have stuff going on and they might just only be watching the recordings, which is fine if that works for you. So we want to look at how do we measure the distance to galaxies and what we can use to be confident in our measurements. Okay, so this is an important picture that relates everything from how we measure our distances from the very edges of the universe all the way to the solar system. And what I want you to notice is that there is overlap of at least 2, if not more than 3 of these measurement methods. And when all 3 methods agree, for instance here, Cepheid, variable stars, and Hubble's law, which we haven't learned about yet, when they work with white dwarf supernova, which we have learned about as a standard candle, and I'll redefine that in a minute, we can be confident if we get the same numbers in this region that where we can't compare them, we are confident in their values. Okay, so that's kind of the key to measuring in the universe. We don't have just one way of measuring things and infer that that must be true. Our confidence in our results comes from the fact that we have multiple ways, independent ways of measuring these distances, and that those methods agree with each other. And that's the hallmark of very good science, and astronomy is pretty good science. So you'll notice we start with the solar system, though, and even though we only have parallax And radar here, these are our most precise measurements, meaning we can do these for many, many things, right? Radar, basically you bounce a signal off something, like if you want to figure out the distance to Jupiter very precisely, you can bounce a signal off of Jupiter and it comes back. You have a stopwatch. You know that the speed of light is constant. I want to write that down. The reason we can do that is because C, hold on. C is constant. That means that the speed of light is always the same, no matter what frequency you use. So if you know the distance, or x, is equal to vt, so we can say that the distance is equal to ct. We have a stopwatch, and we know the velocity, right? So we send our signal out, we start our watch. As soon as the click comes back, we stop our watch, multiply the two numbers together. That gives us the distance. Very simple. Then with parallax, if you remember, we use our Pythagorean theorem to look at how those stars change over the year. And then you'll notice with parallax, which we can do precisely from Earth, that gets us into the low end of Cepheid variables and main sequence fitting, all right, with the Hertzsprung-Russell diagram for a cluster of stars. So we can already have comparisons, and that takes us out to larger distances, and then we get to our large distance standards out at the end. All right, let's focus on each one of these. So radar, again, you just point the dish, beam the object. For an astronomical unit, the distance between the Earth and the Sun, we can measure that almost constantly and get a very precise unit. And everything is built on that astronomical unit. All right, and in fact, most distances are reported in the literature not in light years, but in centimeters. That is the actual measured distance of these things. Now, those centimeters, we don't know these things down to the centimeter, but that's the correct units. With the radar imaging, we actually can get centimeter precision, even nanometer precision, because you can use a coherent source. Maybe not nanometers for radar. That's right. If it were visible, so for the moon, we can use a visible wavelength and get a very precise, like sub-millimeter micrometer measurement. But for radio waves, yeah, we'll get centimeter precision. That 21 centimeters will be what we can resolve. And again, you just send the signal from the dish, it goes out, and it bounces back. And that's all. All right. And now parallax we've gone over a couple times. So you know how this works at this point. If you don't remember, just get your eye. Go back and forth with your eyes. One eye is July, one is January, and that's what you see with near distant stars. You can see them move position relative to much farther away background stars. And from there, you can figure out all the angles. And then once you have the angles and this AU, this distance, you can resolve the other two sides of the triangle. All right, you can get distance right away. You only need Math 115 math to figure this out. We also talked about luminosity. I'll remind you that this alien symbol here is incorrect, and this should read 4 pi r squared, where r is radius. All right, and we can also see that as things get farther away, they are dimmer, right? And they get dimmer with the square of the distance. So we saw that in our previous discussion here, where we talked about brightness and distance and luminosity, right? Where brightness, I'm going to call this L for luminosity, and I'm just going to write 4 pi r squared, where r is that distance, okay? And then we can solve for, we can solve for distance fairly easily, but luminosity, you might be saying, well, wait a minute, how do I get luminosity? Well, some processes, if you remember, have fixed luminosity. All right, you need a fixed physical luminosity. Hold on. Fixed luminosity. All right, so we need to look at processes that can give us a very accurate luminosity that aren't just distance related. And one of those, we know one of those off the top of our head, that's our white dwarf supernova. So our white dwarf supernova, if you remembered, can only happen at a very specific size and mass. And because of that, they always have the same intensity when they ignite. They might not have the same brightness, but they'll all have the same luminosity. All right, so close white dwarf supernova, where we can use the distance through the Pythagorean theorem and the brightness, we can do that to figure out the total luminosity. And then for distant white dwarf supernova, we can use the same luminosity and the brightness we detect on Earth to figure out the distance. And that's what makes it a standard candle. A candle, a source whose power output is known, and that way you can plug those standard candles into this formula, look at the brightness you measure on Earth, and you can get the distance. So we're going to talk about a few of these. So this is an easy example of a standard candle. So you'll notice that these are 3 different lights. Now they're all the same exact candle, so they have the same luminosity, right? But they're different distances away, and you can observe the decrease in brightness, right? So this one, you double the distance, you lose 75% of your brightness from the original. And then if you go 3 times as far away, then you lose 90% of your brightness, okay? So let's take a look at this. So Cepheid various stars are very luminous. So there are these very luminous stars called Cepheid variable stars. And they're in this instability region here in the HR diagram. And basically their brightness will vary either very slowly with a period of days or very rapidly with periods of hours. And when we look at them, hoping we have a graph, good. We can see here the brightness of this particular star varies over 50 days. So that's a long period, right? But we can look at the curve here, and we can measure the period the period of brightness. So here at the peak, this is when the star is the most bright. Here's at the least bright. And as we watch these Cepheid variable stars vary, we can use the period of variation to assign a mass to the star. All right. And then as we can do that, as we can assign a mass to the star, we can also use it to assign a luminosity to the star. And then from there, if we know, again, if we can use these Cepheid variables, you'll notice we have this curve we fit on. If we can fit the star here, then we can use this curve as a standard candle. We can then figure out the luminosity, the fixed luminosity. And then if we have the luminosity and the brightness, we can figure out the distance. All right, so Cepheid variable stars with longer periods have greater luminosities. Okay. So yeah, we saw that. Now we also touched on this, that white dwarf supernova also act like standard candles. Again, we know why, because they only occur under extremely specific conditions, and all white dwarf supernovas are identical in that they all involve white dwarfs of the same size with the same amount of energy, and so you can always use that explosion as a standard candle and figure out its total luminosity. So apparent brightness of a white dwarf supernova tells us the distance of its galaxy up to about 10 billion light years. But we have data from cosmic microwave background radiation, which we'll definitely learn about in another chapter, because that's our one observational cosmic scale object. And we'll also look at, but we have data back to about 11 to 12 billion light years, and that we can use Hubble's constant, all right, which you'll notice starts to vary as those light years get bigger, but not by much. So Hubble's constant is a pure Doppler shift well, it's a Doppler shifted derived measurement. And what I mean by that is you look at the farthest galaxies away, and you can see the Doppler redshift because they're moving away from us in their spectrum. And so once you get that whatchamacallit, that Doppler shifted frequency, you can from there figure out the velocity at which it's moving away. And so what Hubble did is he looked at many galaxies and constructed this chart and noticed that the farther the redshift, the faster away the galaxy was moving. And from there was able to create this relation with this constant called Hubble's constant that you could then extract. Once you had the velocity, you could then figure out where you are on this line. And then from where you are, that would tell you how fast you were moving. And then that would give you the distance that you were away. So it's a pretty simple equation. I don't want to talk about that yet. I want to talk about the Hubble constant. And so Hubble's law gives us the velocity times Hubble's constant gives us the distance. So Hubble's worked this out experimentally with a lot of galaxies. The velocity we can look at from the spectrum because we can get the Doppler shifted velocity. And then all we have to do is if we see a new dot appear somewhere here, we see where it appears here, and we look at its velocity, and that will then, we'll get that from measurement, divide it by Hubble's constant, we get the distance. Now, there's an interesting topic interjected here that is very much worth talking about. And that is, when did we realize that we were a universe of galaxies? Again, only about 1920. So before Hubble and his discovery that we were indeed a universe of galaxies, some scientists argued that objects known as spiral nebula might be entire galaxies like our own Milky Way, whereas it was also a very mainstream position that they were smaller collections of stars within our own galactic structure. And basically, yes, some people did pose the right answer, but they had no means to devise an experiment to answer the question. Hubble devised the experiment and answered the question in 1920. And what he did that by using Cepheid variables with his telescope here. Here's Edwin Hubble. And he was able to measure the distance to the Andromeda spiral nebula by looking at these Cepheid variable stars in the Andromeda galaxy and finding that they were I didn't realize that I couldn't be seen. It was much, much farther away than local stars in our groups. Many, we're talking millions of light years instead of thousands or tens of thousands of light years. So that was a huge discovery, and it made the universe a lot bigger. Or at least our understanding of the universe a lot bigger, right? The universe is the universe. It doesn't really care about us, but our ability to comprehend it grew substantially. And again, I alluded to this, but Hubble did find that galaxies outside our local group are all moving away from us. Okay. So we already went over that. We went over that. Okay. So we already stated this, but that's okay. I like looking at the picture. And again, you can see how all of this now fits with our different standard candles and how we go from measuring local distances to measuring the cosmos. And it's important to understand because remember, if you recall, I told you when we first started this course way back in March that the most fundamental important question is how do we know what we know? So you've seen a lot of pictures of a lot of things. I've told you a lot about the structures of planets, stars, and now galaxies. And the question you should always have is how do we know that? And if you're sitting there telling yourself, well, he's just making this up, none of this is real, or that's all just a theory, or you're dismissing it as not true, that's not the case. We've spent the last 400 years, in particular the last 100 years, building up better equipment that can measure light at lower levels for longer periods of time to create images that reveal new features of the universe to us. And in the last 80 years, we've been able to measure further and farther out. And in the last 30 years, since the Hubble Space Telescope launched in about 1993, we've been able to learn an immense amount about the structure of the universe. But you can see how we construct our distance measurements, our velocity measurements, and they all fall back to interactions of light and matter. And I hope you can see that now here, that's the fundamental building block of how we know what we know. Is the study of physics is a few fundamental things. One of them is understanding very precisely how light interacts with matter. And a full rigorous course on how light interacts with matter, you could spend the rest of your life studying it and not even scratch the surface. I know because I spent a good amount of my life studying it and have barely scratched the surface. So, yeah. So that's where we want to ground all the cool stuff we see, is that we understand how we see it, why it is we can see things with instrumentation that we can't see. That comes from understanding that there's different parts of the electromagnetic spectrum, and the rules by how we classify objects that dictate, for instance, whether something's a white dwarf, neutron star, or black hole. And all these things sort of come together to tell us everything we know about the universe. Okay? So any questions before we move on? Questions, thoughts, answers? Nope. Okay. Good. Well, let's move on to more fun with galaxies. I'm going to move through there. Some more simulations and stuff. Did I miss the beginning to the section? All right. I don't want to talk about. All right. So this should be under the cosmological principle. It's got a little messed up. So one of the things we notice about galaxies moving away from each other is this is to build our bridge to cosmology, which is what we need to do now at the end of galaxies, which is where we are. It's helpful to think of how everything that observation Hubble made, which is that everything is moving away from us for the most part, right? So if you look around, if you look around you and everything is moving farther and farther away from you, if you rewind time instead of push it forward, you naturally come to the conclusion that everything was smaller and more dense and closer together, right? Back at some point in the past. So with that being said, you can look here, so you can sort of see this is the universe today, the universe as it was before, and the universe in the future, all right? And we see that the farther away you are from the point, the faster you are moving away from B, right? So you'll notice the points C and A are one distance away, or it says 3 centimeters, and they're moving away at 1 centimeter per second. But D, point D here, is 6 centimeters from B, and it's moving away from B at 2 centimeters per second. So twice the distance, twice the speed. So what we come to some conclusions about the cosmos, all right? And so the cosmological principle is that the universe should look the same no matter where you are within it. So observations we make that lead us to this assertion: 1, matter is evenly distributed on very large scales in the universe, all right? 2, there's no apparent center or edge. So if you're feeling like you are the center of the universe, in some sense you're correct, but so is everyone else. There's no actual center. So this is not proven, but it's consistent with all observations to date. There's no observation that leads us to believe that this statement isn't true. And we're at a point where sometimes you have to make these statements and recognize that you don't have direct evidence for them, but there's no competing statement, right? There's no competing statement that observations explain that this cosmological principle doesn't. So it's not, you know, I'd say there's, you know, if you're looking at levels of stuff, there's accepted, there's hypothesis. These are things that can be argued. There's accepted hypothesis. And then there's experiment. There's theories that has experimental validation. So the phrase "it's just a theory" makes no sense in actual science, because theory is the highest sort of level you can get to, right? And that's where you have experimental validation. Accepted means there's no experimental proof or experimental validation, but there's no observational, there's not a lot of, it's a statement like this one, the cosmological principle would fit here, right? Because it's one of those things that there's not any observation and not a lot of argument against it. There's nothing that says this is a bad idea, but it's certainly recognized that it's not an experimental verified fact, right? Because we haven't been to other places in the universe. Now, a hypothesis is usually the bread and butter of science, right? So a good example of a hypothesis that we just saw was the discussion between spiral nebula as groups of stars within the Milky Way and as galaxies that are separate structures beyond the Milky Way. Right? So that's a good hypothesis because there are two very vigorously argued sides, but no experiments to prove them. And so because you could argue one way or the other, we had to leapfrog accepted hypothesis, and then we were finally able to do, or Edwin Hubble was finally able to do experiments that got data. And all of the data went with one side of the argument, and none of it went with the other, right? Which was the spiral nebula side. So therefore, you very quickly can, in that case, go from a hypothesis can now turn into part of a theory. All right? So that's important to look at. Now, distances between faraway galaxies change while light travels. This makes looking at the actual length of the universe rather difficult. So let me sort of write what I mean here. So we know that the distance is equal to c times t, right? That's our distance, speed of light, and our time. Now, we know that the age of the universe is equal to about 13.7 times 10 to the 9, or billion years old. All right? Now, the weird thing, though, is that the diameter of the distance of the universe is nearly 100 billion light years. So a fair question is, well, wait a minute, if the universe is only 13.7 billion years old, then the radius should be 13.7 billion light years, and the diameter should only be around 25 billion light years. And that would be right if the universe was expanding into something. But it's not. It itself is just expanding, or at least whatever the something is it is expanding to is not something we can perceive or measure. So what I mean by that is when you look at a light source heading towards the Milky Way galaxy and getting to Earth a long time ago, they had a fixed distance. Now, if the universe only had this diameter, this 25 billion light year diameter, that would mean that the same distance exists between these two today. All right? But that's not what's happening. What's happening is that the universe, it's not just that these are moving farther away from each other, the universe is actually expanding, increasing the distance, and stretching the light that's emitted. All right? And that's what we can see is that space-time itself is getting bigger. That Doppler shifts this signal, and so now our distance away is d2. So it is actually possible, because the speed at which these faraway things are moving can exceed the speed of light. And so what that means is that these two, even though they could share information at one point, today they are not causally connected. And that means that eventually we will lose all information about this galaxy. Okay? So we'll learn more about that when we talk about the expansion of the universe. But that's what's going on there. So we usually do things when we talk about distances in the universe. You'll find we often talk in look-back time, because it's a little hard to wrap one's head around an expanding universe, this dynamic system. So we just talk about, you'll notice I say this galaxy is 12 billion light years away from when the universe was only 1 billion or 2 billion years old. That means we're using look-back time as our paradigm for distance, not physical actual distance, which can be confusing, but you know, science, isn't science fun? So yeah, so that's why, and you'll notice they make this point here, right? That astronomers think in terms of look-back time rather than actual distance. All right, because the distances between galaxies change. All right, good. Glad someone's enjoying it. So let's see. Any questions about that? About our distance changing? I'll say it again. The distance between the galaxies is actually changing. All right, so that's why hard distance doesn't work. Look back time remains much more static. Okay? So just let me know if anything is troublesome. All right, so why don't we take a short break, because we have had a lot of information and I don't want to just power through for the next hour, but I think I do want to finish this chapter if possible. So I have you till about 6:50, I think. So let's take a 10-minute break and come back at 6:05, and we'll get through as much of the rest as we can. I'd like to finish it, but if we don't, it's not a big deal. I just want to give you some time for the information to sort of sink in without throwing it all at you. So I think a little brain break will be helpful here. Okay, so I'll be back around 6. All right, back. We're back. Indeed. Okay, let's go forward. Oh, we already explained this, but what we were looking at is how light changes as the universe gets bigger. And you can see that as the universe expands, that wavelength is stretched, changing the frequency, and that's the source of our gravitational redshift. I thought we'd finish that. Oh well. So now what we want to look at is galaxy evolution, okay? So galaxies are kind of interesting because we can see what happens to galaxies when they run out of fuel, but we can't see what happens to a galaxy when it loses all star formation because the universe isn't that old yet. All right? So we'll look at how do we study galaxy evolution. We can study from long look back time ago to current times. We'll again look at some of the different features in which ways in which galaxies differ. We'll try and look at the mechanisms that might cause that. And we'll also look at how gas cycles through galaxies. Okay? So again, you'll notice when we look at the young galaxies, there's a lot of irregulars. There's a lot of weird stuff going on here. And then at about 4 billion years, our current structure takes its shape. And you want to note that there's not a ton of information in this low past 2 billion years era. We really need infrared and James Webb to get more information on this era of the universe. But we start to see small ellipticals and giant ellipticals, and then these evolving complexity in structural and spiral galaxies. And then, of course, we do see a lot of more defined irregular galaxies. All right. So what do our deep observations tell us that show us distant galaxies as they were earlier in time? All right, this goes back to that look back time idea and what we've been talking about. So when we see something here that we say it's from 12 billion light years away, it's what it looked like 12 billion years ago. Okay, so but everything's just a little more extreme there. Now, this is what I meant when I talked about how I didn't quite like that protogalactic cloud model, because when we look at galaxy formation, you'll notice you have a progression of galaxy formation here. And you'll notice that protogalactic cloud takes place in a universe that is far smaller and everything is far closer together. So sure, there will be different regions of higher gravity versus lower gravity, but you'll notice I like this set better because even though you do see that individual galaxies flatten out with the conservation of angular momentum eventually, what's almost more interesting is that you can see the large-scale structure of the universe occur as a cloud like this, nearly uniform cloud, becomes less uniform and squeezes into this sort of veiny structure, large-scale picture of the universe. And when we look at this large-scale universe, it does look like this. All right? But again, we have to do that mostly in infrared. And so again, when we talk about that simplified model, we're going to have to add other things, more mass, that we'll talk about next time and the time after in our final lecture, where we get things like dark matter and involve that in the formation of these galaxies, which will squeeze this cloud into these sort of channels and web-like structure that we see. So they start here with these protogalactic clouds, but what's not clear to me is that are all protogalactic clouds the same protogalactic cloud if the universe is much smaller? I don't know. That's something I've been trying to work on. And of course, the leftover gas, I think when you look at here, you might have your protogalactic clouds, they expand out from each other. They're going to get squished in, and then that angular momentum conservation will create those flat disks that we see. However, galaxies end up, as we saw, looking vastly different. Even among spiral galaxies, there was a ton of variation. So why do they end up looking so different? Well, one idea is galaxy collisions. Now, this is a a picture of galaxy collisions. This is actually a little more fun to look at on YouTube. So I'm going to give you a link. I'm going to try and find one. Yeah, galaxy collisions. Collision simulation. So let's look here. So I'm going to give you 2 or 3 minutes to look at this. Oh, that was not smart. See, back to this. So we want to watch this video, copy that link, and we'll come back in about 2 minutes. It's a short video. Very likely that's what happened to the tadpole galaxy, right? It's still in the process of this collision process. So it sort of looks like this now, right? That sort of looks like a tadpole. We might only be seeing it from a vantage point that that makes it look like a tadpole. But I mean, I don't know specifically that one, but that's what I would suspect. That it's somewhere like here. As you can see, probably not. Galaxy collisions take a few million years. Remember, in a universe where things last and have processes going on for billions of years, millions of years isn't very long, but it's not an instant collision like, say, a neutron star or 2 black holes. You definitely have these things whirring around each other for a very long time. Because again, they're so vast and huge. So yeah, it takes a couple million, I think 10 or 13 million years for galaxies, for 2 sizable spirals to finish colliding. Interesting fun fact, the distances between stars are so great that the chances of individual stars colliding during this process are virtually zero, non-existent. The gases collide, and that's what happens, but the stars themselves don't actually collide. They might get thrown away, they might get like ejected, but they won't. But I guess what I'm trying to say too here is like our existence is predicated a lot more on the sun than our galaxy. So if we were to get thrown out of the galaxy, I mean, you know, it might suck. Well, who knows? It might be pretty spectacular if we saw the Milky Way just sort of dominate the skyline at night. But that being said, you know, it's not going to affect us too much, just how many stars we see. Well, once the gas ignites, it heats up and creates a massive episode of star creation. But then it's thought that once these spiral galaxies are finished colliding, you'll notice you have something that looks like an elliptical galaxy. And it's thought that ellipticals come from these collisions of small spirals. And that's what that's the current working hypothesis. There's some evidence there's some good simulations that support this, where you can start with 2 spirals and a lot of different variations end up with an elliptical. So it's very likely that the source of many elliptical galaxies are small collisions. But you'll notice that instead of saying it is like, it's this, I'm saying it's likely, probably, because we're getting into that realm where our models make good predictions, but the fun thing about astronomy is you never know what you're going to find with the next telescope, or what model you'll find that, you know, has a much better explanation than the previous ones. One of the fun things I hope you'll find from this course after you finish taking it is that about once a week there's something very interesting and astronomy related in the news, in the newspaper. There's even been stuff during the coronavirus. It just doesn't make the main news. I mean, astronomy never makes the main news, but if you look up space news, you'll find there's been stuff going on, and every week something very interesting or new is happening. It's a science that's very alive and active and is often accessible. So I encourage you to keep up with it. So conditions in the protogalactic cloud, I think the question mark is the right answer here. But initial angular momentum of the protogalactic cloud could determine the size of the resulting disk. I'm reading this out loud because I want you to notice they're using the same language I am. Could, might, likely. Elliptical galaxies could come from dense protogalactic clouds that were able to cool from stars, meaning we have models in which these things lead to what we see, but it's not unreasonable to think there are a few models that give you the right answer. And the question is, if they have differences, can you test the differences between those two models to figure out which one is right? So let's see. Observations of some distant red elliptical galaxies support the idea that most of their stars formed very early in the history of the universe. Okay. And we must also consider the effects of these collisions. This is a bit more, this is a live picture of a collision, right? This one's going on right now. Well, I mean, it's not going on right now, but our ability to see it is occurring right now. Is the more correct way to say that. We've talked about this, and that is, if you go back, collisions are more likely in a smaller, denser universe than they are in a modern, you know, where the less dense, bigger universe. So again, someone asked about star formation. So short bursts of star formation will occur in colliding galaxies. You can sort of see that it's highlighted here in this colliding galaxy. But that'll sort of be like, imagine, it's sort of like if your life, you had so many set experiences, right? You can either have all those experiences over 100 years or over 30 years. So basically, your lifespan gets very shortened, and all of their gas, their potential, is used up in, you know, a short amount of time, relatively speaking, short amount of time for galaxies. So again, these collisions show that it is possible to make an elliptical from the collision of two spiral galaxies. And that may explain why in these large clusters, these highly dense galaxy clusters, you see tons and tons and tons of elliptical galaxies and only a few spiral galaxies. All right. So again, you're going to notice this fascinating picture around these galaxies. It says these bright clumps of stars were once the centers of smaller galaxies. I want to see if it's pointing out the lensing going on. We'll talk about lensing as evidence for dark matter, but I want you to notice it's apparent in these pictures. So it's sort of, there's some evidence that indicates here that in these giant globular clusters that some of these centers are close together from several galaxies. And now we want to look at gas cycling through galaxies. So as gas, so basically what we looked at is the galactic recycling program sort of gives you it gives you the lifespan of a galaxy, right? Galaxies are alive as long as they can form new stars. So all galaxies begin, or are thought to begin, are blue and white in color, and with these galaxies being the young galaxies. And then as time goes on and collisions happen, you end up over here in the last leg galaxies, all right? So these galaxies merge to produce larger, more luminous systems that become red as star formation shuts off. So all the gas is used, and these can be very bright, but their color is not blue or white or purple because there's no active star formation. All right. What I'm hoping you see from this is that the same amounts of information tell us a surprisingly large amount of information, and this is one of those reasons physics sort of is what it is as a science goes. It really is the best of the sciences in as far in the sense that it very frequently gives you a tremendous amount of information with just a little tiny bit. Chemistry and biology are important, but you need to keep expanding, and every niche in those fields can grow rather large. Whereas in physics, we certainly have large niches. I'm not saying we've escaped that, but we have a few small principles that are very elegantly explained mathematically. And I hope you see the themes like star color. Star color can tell us how old a galaxy is. It can help us determine, gives us a structure for arguing how a galaxy evolves. And that's just the color of the star, right? It's just one thing that tells you all this stuff. We can also use that light from the color to see its redshift, to see how far away the galaxy is. So this one thing tells you a tremendous amount of information. But let's get back to different types of galaxies. So what you're looking at here is a starburst galaxy, which forms stars so quickly that they use up all their gas in less than 1 billion years. So this is a galaxy on an accelerated life frame. Okay. Now, the intensity of supernova explosions in starburst galaxies can actually create and drive what we'll call galactic winds. So these are winds between galaxies. Some of this heated gas may eventually fall back and cool back into the galaxy, but if the wind is strong enough, it'll just take it all and blow it out away. We can see an X-ray image. These are the intensity of supernova explosions in starburst galaxies. Here you can see more of that wind being driven parallel to the disk, or perpendicular to the disk, sorry. I'm losing my words because it's 6-ish, 30-ish. So, so we can see that. And now we want to talk about our final feature of galaxies, which are these supermassive black holes. All right? So these supermassive black holes seem to be at the center of galaxies. And again, we talked about the 4 million solar mass black hole in the center of our own galaxy. Some of these become truly spectacularly big. So if we look here, first we want to say, well, what's some more evidence of these supermassive black holes? Well, there are these enormous jets in active galactic nuclei, or quasars, that could only be the only source to get energy, this much energy to create a jet this big, would be a massive gravitational source that could heat up large amounts of matter. And the object would have to be much bigger than a sun or any star. It would have to, again, very clearly exceed that 300 solar mass limit. So something like a 4 million solar mass, like at the center of our galaxy, would do it, but we're going to see these can get even bigger. And in the early universe, we see these active galactic nuclei, and when they're very luminous, which the luminous ones were discovered first, these were called quasars. And quasars, as this object of study, have only really been studied since the 90s. All right? There were hints of them, but we really needed the Hubble telescope to really study them in detail. All right? So now let's see why we think this the way it is. Now, remember, the brightness of there's a few things. The distance indicates from these quasars, their redshift indicates that they're all very, very far away and in the early universe. But here's the crazy part. The brightness and distance we find of the luminosity from some quasars exceed 1 trillion solar luminosities. Now, I want to express to you how big that is. If you remember, the sun, so just where that number is 1, exerts enough energy to power all of human civilization at our current level for 1 million years every second. So a quasar has enough energy, expels enough energy every second to power humanity for 10 to the 18th years. That is bigger than a trillion, and that is bigger than a quadrillion, which is 10 to the 13th, 14th, 15th, and it's actually equal to a quintillion years. All right, so wrap your head around that number. Now, the variability of this brightness shows that all this energy comes from a region smaller than the solar system. So we have an object that is compact, but is a trillion times more luminous than the sun. And they only take place in the early universe, thankfully. There'd probably be too much radiation for us to survive if our galactic nuclei were that bright. So here we see a picture of the first object to be identified as a quasar with a luminosity 1 trillion times that of the sun. And that is very far away. And the accretion disk of this object, which appears to be a supermassive black hole, is the only way we have within our current models of physics to explain this object. And there are even more intense objects in the universe too. Some we can't even see the effects of, like the Great Attractor. But more on that in a little bit. So the orbital speed and distance of gas orbiting the center of this galaxy, M87, indicate a black hole with a mass of at least, on the low end, 3 billion solar masses. So there's an object, there are objects with billions and billions of solar masses in these compact areas that could create these quasars. All right, and if we were around one, we'd either, so massive black holes are a little more gentle, but that's a lot of sun to be drawn into. And if you could use that as an energy source, you would have truly unlimited energy. You know, talk about cheap, free power. Maybe not cheap, but certainly free. The gravitational potential energy of matter falling into the black hole turns into this kinetic energy, which speeds up the particles that are going towards it. Friction in the accretion disk turns that kinetic energy into light, right? Friction heats things, raises temperatures, heats things up. And this process can convert 10 to 40% of that energy into radiation. And that's what we see. And in order to get the radiation that we see, Einstein's equals MC squared kind of lets us work this backwards to see how much gravitational potential energy we're going to need. And that's where we get our billions and billions of solar massive black holes. Do supermassive black holes regulate galaxy evolution? It's a good question. Many nearby galaxies, and perhaps all of them, we have found that they do have supermassive black holes at their center. These black holes seem to be dormant in our neck of the woods, but we're at a more local, time-wise picture of the universe. And it's hypothesized that all galaxies may have passed through a quasar stage earlier in time, but it's hard to say. And there's actually some interesting articles that show that the nuclei might spin up and spin down, and that our galactic nucleus may have been active as early as 2 or 3 million years ago. So I think it was 2 or 3 million. It's a recent article, but you'll have to look it up. It was pretty fascinating. So the mass of the galaxy's central black hole is closely related to the mass of the bulge in the galaxy. And we can see here that they state that it must somehow be evolved, but the connection to how these central black holes affect galaxy evolution is still very much an open question and still being heavily researched. We don't have answers yet, but we're getting there. We don't know when we will have them. But you can see these lobes from these galaxies, these giant lobes. Now, keep in mind, these lobes are hundreds of thousands of light years big. These are huge objects, and they come from this tiny center of this quasar. And we can see that. And that's basically it for tonight. So I thought we might end early, and we have. No reason to start the new chapter. So I'm going to take attendance very quickly. Keep up with your quizzes, please. They have been and are up. And yeah, don't forget to do your general relativity assignment. That is also up. And you will, I promise, I know I've been promising for a while, but your grades really must get done. So they are the highest priority. So I'll try and grade something tonight, so you have something to look at. The only big mistake that could really be made is if you turned in the worksheet for Lab 1. But please be aware that whatever I do grade, you can revise. But I realize we're quickly running out of time to revise. So I got to get on that, and I'll get back to you on it. Margarito, did you have a question? I can't hear. My volume seems to be down, and I can't find my remote control.
No, I don't have a question.
Oh, okay. All right. Good, good. All right. Well, if you guys have questions, I'll stick around in the room for a little bit. I'm going to turn my camera off, but I'll leave my microphone on. You might need to speak a little louder because I put my remote control somewhere where I don't know where it is. But I'll be around till around 20 till. My mic on, and I gotta find this.
All right, see you later, Professor.
See you later. All right. Now, where is this remote? Oh, hold on. Oh, there's the record. It was right in front of me the whole time. Jeez. All right. That was the wrong button. Okay. Blackboard. All the grades will be on Blackboard. Yes, you'll be able to revise. Yeah. And basically, as we run out of time, I will be more lenient in my grading. I expect most of these are good. The biggest mistake is that people turn in the worksheet, and then they just redo it. I get very few revisions in this class. I'm just saying in general. I'm not saying you can't do one. I'm just saying I usually don't get them, because you guys usually do a pretty good job once you get the format down. And you don't just write the worksheets. Yep, no problem. Nope, I haven't posted grades yet. That's coming soon. You too. I can't get my fruit roll-up out. This is frustrating. All right. Oh, you were telling me about this, Alcides. I'll watch Anderson Cooper report on it afterwards. Unidentified aerial phenomenon. Total of 10 quizzes, yes. The last quizzes will come out as the final exam. So, and they're going to come out. Yeah, well, you were supposed to send me the link. I finally got it. So I'll look at it and I'll have an opinion on Tuesday. And keep in mind, everyone, that we will be meeting on Tuesday. I just want to be sure I don't have to correct myself on that. Hold on. LaGuardia. Ask LaGuardia, my LaGuardia, search academic calendar. Yep, it says irregular day for Tuesday, May 26th. Classes follow on Monday schedule, and on Monday the 25th, we can enjoy a brief break. So yep, so that's what we're gonna do. All right, so I'll see you all on the 26th, not the 25th. Okay?